Hi everyone, welcome to the TamTech Academy channel. Today we are going to talk about pump design or pump sizing, which is a key topic in chemical and process engineering. So choosing the right pump is crucial for both safe and reliable operation and at the same time energy efficient fluid transport. So you should follow a clear step-by-step process to do it right. Let's go through the main steps together. So step 1 is collecting initial data. It includes flow rate, composition, density, temperature, viscosity, vapor pressure, and etc. These affect how the fluid flows and how much energy is needed to move it. But at the same time, we need system details like pipe diameter, pipe lengths, fittings like valves, elbows, and etc. Sometimes not all data is available. That's why as an engineer we need to make assumption. It should be based on our experience or reliable source from literature. After labeling all initial data, we need to calculate some requirements in order to know that whether our fluid is laminar or turbulent. So we will use here Reynolds number to determine our fluid is laminar or turbulent, because at the end it will affect the friction factor and pressure losses. So for finding Reynolds number, we need velocity. Velocity comes from this equation, which is called continuity equation, is equal to flow rate divided by cross-sectional area. And if we don't know cross-section area, we will find it from PD squared divided by 4 equation, and we'll put it to here and found U. After finding U, we will find Reynolds number, which is equal to density multiply velocity of the fluid multiply diameter and divided by viscosity of the fluid. After finding Reynolds number, we will calculate relative roughness, which is equal to absolute roughness divided by diameter. We will use these two parameters in order to find friction factor from the chart. I will show it later on. So next step is calculation of pressure losses. As fluid moves, it loses energy due to two factors. First one is major losses. It's lost because of friction along the pipe, and minor losses, it's valve, elbow, or other fitting. To calculate total head loss, we need to know both major loss and minor loss. For minor losses, we can use two methods: lost velocity method and equivalent length method. If it's interesting to you, you can put comment below and we will share video related to our major and minor loss methods. But all in all, we can use here friction factor multiply length of the pipe divided by diameter, which represents major losses, but this is representing minor losses. LE divided by D, which is found from chart, table, and summation of them, multiplication of it to friction factor and U square rho divided by 2 will give us total head loss. And in order to find F, as I mentioned beforehand, we need Reynolds number and relative roughness. For this chart here, you can see in this axis we have Reynolds number, but in this axis we have pipe relative roughness. As you can see here, it's E divided by D. By intersecting them, like Reynolds number and pipe relative roughness, for example, like this, if it's our relative roughness, we will find F friction factor and we'll use it in finding pressure loss. And after this step, we come to again some calculation steps, and here we will do same process twice for suction side and for discharge side. For suction side, head is equal to suction vapor pressure divided by rho g plus H, which represents static suction head, and minus HFS, which is head loss in suction side. And we will do the same for discharge, which is like same process. Here we use discharge pressure divided by rho g plus static discharge head and plus head loss in discharge. and we will find these two parameters, and we'll use it to find HP, which is pump head. Pump head is equal to discharge head minus suction head, and we will multiply heat density and G in order to find pump total pressure. And if they ask about pump power, we can use this two equation. So here you can see it's equal to flow rate multiplied by pump pressure. But here we have additional efficiency factor. Why we put it here? Because in like this is for hydraulic power. But if you want to find shaft or motor power, you need to divide it by pump efficiency. And at the end, we need to calculate MPSH available. We have two types of MPSH, net positive suction head, which are available and required. MPSH required is given by vendor, but MPSH available is calculated by process engineers. So here you can see it's suction side pressure divided by rho G plus H elevation minus pressure loss divided by rho G and minus vapor pressure divided by rho G. We will find MPSH available at the end. So MPSH available should be large than MPSH required. If it's larger, if MPSH available is larger than required, then it's good to go. Like we will have no cavitation zone. But if MPSH available is smaller than MPSH required, we will move to cavitation zone, which is undesirable for pump design. That's why we should like do our design steps again. So that's all from pump design steps. If you have any question, you can drop your question to our comment section and we will answer them promptly.